Hello everyone, welcome to EkEdu. So in this video we have to study about the color in the coordination compounds. What happens? Suppose we have a compound like this. We have titanium H2 whole 4 3 H2 whole 6 3 plus. This is our complex compound, right? So what happens? Let's first write down the titanium's oxidation state. See, titanium in its ground state is 3D2 4s2, and if titanium plus 3, it means it is 3D1. Now water, we know that water is a weak field ligand. Let's draw the, see, this is 5d orbitals. Now what happens after splitting? We have T2g orbitals and EG orbital. This is the ground state I'm drawing. So here the electron will enter here. But what happens when we apply energy? Yes, when we give it some energy, what happens? The electron jumps from this T2g orbital to EG orbital. So we get one electron here. So due to this, what happens? Due to DD transition, we can say due to DD transition, we observe color. We can say color is observed in coordination compounds. And how? I'll explain you. Suppose how to learn it. See, we have this right here. Suppose this is, remember Vibgyor, color of rainbows. Vibgyor. Now what happens in case of titanium H2 whole 6? What happens? Suppose the color, yes, the color is, suppose the color which is being present, right? Suppose the color being, now suppose the color is green. Let's suppose the color is green. Now what happens? After absorption of energy, it gives complementary color. Can you see the complementary color to green is red? So this is how what happens. Means after the absorption of energy, when the electron jumps from T2g orbital to EG orbital, what happens? The complementary color, we observe a complementary color. Suppose here we have T2g1, but here we have EG1. So after the absorption of energy, the complementary color is observed, and we know that as we move from violet to red, as we move like from violet to red, yes, what happens? The wavelength lambda increases. Yes, that is why you must have read in your junior classes also that red color has the longest wavelength. Yes, that is why, this is the reason behind sunset. Whenever sunset takes place, we observe red color. So as we move from this towards red, lambda increases. The value of lambda increases. And as we move from red towards violet, what is the concept? What is this? Energy E equals to hc by lambda. So this side, on the reverse side, energy will increase. Yes. For example, one question had come in exam. I'll show you the question. See, they had given us 4 complexes and they had asked which of the following will have, you have to arrange them in the increasing order of their wavelengths. Arrange them in the increasing order of their wavelength, lambda values. So the complexes are COH2 whole 6, 3 plus, COEN whole 3, 3 plus, and we have CuNH3, NH3 whole 6. I'll explain the concept here on all itself. See, energy is equals to Hc by lambda, right? Yes, energy is equals to Hc by lambda. So we know that this is a weak field ligand. These both are strong field ligand. These both are strong. So in weak field ligand, Scott Walker Manfi Co. D6. Weak field ligand, and these two are strong field ligand. D6. We know that the CFSE value, the CFSE values for strong field ligand are higher. Yes, it's higher for strong field ligand as compared to weak field ligand. Therefore, I can simply write it as, if I arrange the order of energy, increasing order of energy. Energy means CFSE values. So it will be cobalt energy values. Just a minute. The energy value will be, like, if we calculate D6. Just a minute. Let's try to calculate the CFSE values. First, weak field ligand will be T2G, EG. So 1, 2, 3, 4, 5, 6. And this is for weak field ligand. And for strong field ligand, it will be, for strong field ligand, it will be 1, 2, 3, because pairing occurs. So it's T2G. Yes. So what happens if I calculate the CFSE value? In this case, I know this is minus 0.5 dello and this is plus 0.6 dello. So 4 4s are 16 minus 1.6 dello plus 6 2s are 12. So its value is minus 0.4 dello, and its value is for this, its value is 6 4 minus 2.4 dello. So which energy value is higher? It's for weak field ligand. Minus 0.4 is higher than minus 2.4. Therefore, we can say weak field, the energy values for weak field ligand is higher than that of strong field ligand, and so it will be energy order. First, we'll arrange the energy order. It will be highest for COH2 whole 6, 3 plus, and out of ammonia and En, we know that En shows chelation. So it's the strongest ligand, right? So this is the order of energy. Now what will be the order of lambda? Lambda values. It will be reverse. Why? Because we know that E is equal to Hc by lambda. So this is the order of lambda. I hope this much is clear to you. Yes. Now the next, this is all about color in coordination compounds, right? This is all about color in coordination compounds. Now what we have to study is here stability of coordination compounds, how the coordination compounds become stable in nature. Stability of coordination compounds. Now what happens in this case for the stability of coordination compounds? What happens? Suppose we have a metal atom. A metal atom interacts with ligands and it forms a coordination complex, right? Now this coordination complex, right? See what happens here is this coordination complex, it will be formed in various steps, and greater the value of larger is the stability constant, higher will be the proportion of ML4 that exists in solution. I'll explain you how. This takes place in various steps. Suppose M plus L gives you ML. Suppose the rate constant for this is K1. Its value is ML upon M into L, right? Next we have second step. These are the rate constant, and what happens? The metal Metal, there always exists a competition between ligand and solvent molecules, and since ligands are stronger than the solvent molecules, therefore they simply replaces solvent molecules. That is why we simply ignore the solvent molecules. We don't consider them. This is rate constant of second step, which is ml into L. Third step, plus L gives you ml3. Its rate constant will be K3 will be ml3 upon ml2 ligand. And last we have ml3 plus ligand gives us ml4, right? ml4. So K4 will become ml4 by ml3 into ligand. Now if we simply add the 4 steps, if we simply add, these gets cancelled, this will get cancelled, this will get cancelled, this, we will get the first equation, or initial equation. That is metal plus 4 ligand gives us ml4. And we can simply write down the overall stability constant by beta, which will be K1, K2, K3, K4. But means overall stability constant we can calculate by multiplying the rate constant of each and every step. This is overall stability constant. This is beta is overall. I'll write it here. What is beta? Beta is overall stability constant. Larger the value of beta means our complex is very much stable. Overall stability constant. Next we have last point, we have K. This K1, K2, K3, these are, what are these? These are stepwise. Yes, these are stepwise stability constants. These are stepwise stability constants. Next, yes, next, so larger the value of stability constant, more stable will be the complex. This was actually the last topic of the chapter. Now, just a brief, quick review, like is the application, or you can say importance of coordination chemistry in our life. Yes, why do we? It's why the study of coordination chemistry becomes so important. So applications of coordination compounds, or you can say importance of coordination compounds. Importance and applications. We'll quickly go through the applications. Yes, and you can also do these applications from your book. Now what happens? The first is the coordination compounds. Yes, they are found in many qualitative and quantitative chemical analysis. They are found in many quantitative and qualitative chemical analysis. For example, we have complexes like EDTA. Yes, and we have DMG. If we have these complexes like this, what happens? These complexes, you can say kinetic ligands, they are formed as a result of coordination entities, and using this we can estimate, we can use them for detection by some instrumental methods. So this forms the basis of, yes, these complexes form the basis of qualitative and quantitative analysis of various chemical compounds. We use them for various instrumental methods. In various instrumental methods for qualitative and quantitative analysis. Next, very important method, or you can say application. This these coordination compounds are used for the removal of hardness of water, for the removal of hardness of water, for the removal of hardness of water. For example, we know that we have sodium and magnesium ions present inside water. So what happens? They form stable complexes with EDTA. Yes, they form stable complexes with EDTA, and thus they can be easily removed. This is sodium and calcium. They form stable complexes with EDTA, and thus they can be easily removed. Like we know that Na2EDTA, it's a very stable complex, and thus the hardness of water is removed. Yes, and calcium and sodium, they can be removed because they have, due to the difference in the stability constants. Third point, we can use this coordination compounds for the extraction of gold. Like I have taught you in the sixth chapter also how to extract gold. We can use this coordination compounds also for the extraction of gold. Yes, how, like what happens? Gold, it combines with cyanide ions in the presence of water, and therefore it forms a complex. Yes, and this complex can be separated by the extraction methods that we have studied in. Yes, gold soul, this can be separated from the uh, like this like the extraction method that we have studied in the sixth chapter. Fourth point, similarly for the purification of metals, suppose we have purification of metals. Like we have done this method in sixth chapter also. Like suppose we have nickel, so we want to purify nickel. How will we purify? First, nickel carbonyl will formed. Yes, nickel carbonyl will be formed, and this nickel carbonyl, it will decompose. Yes, nickel carbonyl will be formed, NiCO whole for nickel carbonyl will form. This by heating this nickel carbonyl at higher temperature, will get our pure metal back. Next, coordination compounds, they play a very vital role in our biological systems also. How? We have discussed a little bit about it. Biological system also. How? Like I've told you, like we have we have photosynthesis. Yes, chlorophyll we have. Fourth is purification of metals. Purification of metals, like we have nickel carbonyl complex. Yes, if we heat this complex, what will happen? We will get our nickel metal, pure nickel metal back. In biological system, how? Like we know photosynthesis is very necessary for the survival of plants. Yes, so chlorophyll is the pigment which is necessary, right, for the process of photosynthesis. In this photosynthesis chlorophyll, we have Mg2 positive ion, as well as we have porphyrin rings. I've told you the structure of porphyrin rings. So what happens? You don't have to remember any structure. Chlorophyll, what happens? This chlorophyll, as these ions are present, so it's also, they form coordination compounds. Yes, chlorophyll is itself a coordination compound. Next, we have hemoglobin. If I talk about hemoglobin, right? If I This is chlorophyll. Next, we have hemoglobin. In hemoglobin, we have iron. Yes, so iron plays a very vital role in our body. So we have Fe2 plus iron. Next, yes, we have cyanocobalamin, which is vitamin B12. Vitamin B12, which is again very essential for our body. In this, CO2 plus ions are present. CO2 plus ions. So these ions, that is the coordination compounds, are very important because they are very vital. The ions which are present inside the coordination compounds, they are very vital for our biological system, right? Another, we have enzymes, like we also have some enzymes, like we have carboxypeptidase. It's also a coordination compound. And we have carbonic anhydrase. So they also are coordination compounds. Next, next is number 6. We use coordination compounds. They are used as catalyst in the industrial process. For example, a very important and famous catalyst they use as catalysts in industrial processes, and a very famous catalyst we have Wilkinson catalyst, which is Wilkinson catalyst. You should remember the formula of Wilkinson catalyst. Its formula is pH3P pH3P whole thrice RH rhodium Cl, and it's used for hydrogenation of alkenes. It's a very famous catalyst. In one of the exams, they had asked you, like, you had to match the columns. So you had to match the formula of Wilkinson catalyst. That is why it's important to remember its formula. Next, we have, we use coordination compounds, like in black and white photography also. Another we have, yes, we use chelate ligands. Yes, or you can say we use chelate therapy in medicinal industries. We use chelate therapy in industries, like how I've told you earlier also, we have cisplatin. Yes, cisplatin is used as an anti-cancer drug. So this is also a coordination compound. Yes, we use EDTA. If somebody gets lead poisoning, for the removal of lead poisoning. So this is how we use different complexes, right? Other uses you can read from your book. For the removal of excess iron ions, if some excess ions are present, so you use penicillamine. So this is all the uses of coordination chemistry. I hope the applications of coordination chemistry are clear to you. Yes, we have discussed the stability of coordination compound and the color. How the coordination compounds, they show color. The main reason is due to TD transition. If you see, the electron simply jumps. Yes, it simply jumps. After absorption of energy, it simply jumps. And after, when it comes back, yes, so after absorption of energy, when it comes back, right? So what happens? It gives complementary color. Like you have to, like for red, if its initial color is red, it gives after excitation green color. If it's orange, it will give blue. If it's violet, it will give yellow color. So this is how complementary colors work. I hope the topic is clear to you. See you in the next lecture with a new chapter. Till then, bye bye.